for a particular disease, it may not be possible to test the drug with any human beings, or nowadays not even with animals. Earlier, people used to try with rats and mouse. Nowadays, wildlife people will come and protest, so therefore we cannot test on a physical way. So one most inexpensive way is to make a mathematical model of the system. Then in the mathematical model, there may be various parameters, various functions, various variables coming in, and you change those variables and parameters and then see how the system is behaving. That can give us an insight of how the system will behave. Okay, so let me start with what is a system. As a definition, a system is an organized collection of components or entities that interact together to accomplish an overall task or overall goal. In a system, there will be inputs that could be raw materials, and there's a process inside, and which processes these raw materials, and finally we get an output. The system has the inputs which has to undergo these processes to produce output. So the system is is an input-output relationship and a processor inside. And in system study, the major tasks involved are, one is system modeling. So we need to model the system. Another one is system analysis. Okay, analyze the system with respect to its behavior, in terms of time, in terms of various inputs, in terms of various environment. And also in the system study, one is concerned with the system design. If a system is not performing to the level of which we are in need, we have to design, we have to change the components, we have to redesign the system. So system design is also important in the system study. And all these things can be made very easily by system simulation. Now with the invention of new, powerful, very fast computers, we can simulate the system and draw some conclusions which can be made use of making or designing, redesigning the system. So system modeling, system analysis, system design, and system simulation, they're all playing vital role in a system study. Then mathematical model. In system modeling, we want to make a model of it. And one can make a physical model of a system. That's again quite expensive, and time is involved. So therefore, the most effective way nowadays is to model a system in terms of mathematical equations, okay, which is known as a mathematical model. A mathematical model that describes the states or the dynamics of the system by a set of variables and a set of equations or inequations that establish a relationship between these variables. So therefore, a mathematical model is just mimicking or just trying to translating the working of the system in terms of mathematical variables, in terms of functions, in terms of equations and inequations. So thereby you obtain a mathematical model. Now, a mathematical in the system itself could be a dynamical system or a static system. A system is said to be dynamic system if the system variables or the states of the systems are changing with respect to time. If there's a change in the system attributes or entities with respect to time, we refer such system as a dynamical system. Okay, now today I'm going to present to you a system that is modeled in terms of differential equations. Okay, modeling by differential equation, when it happens. So when can you model a system in terms of differential equations? A system can be modeled in various forms. One is a differential equation, one form is differential equations, could be in integral equations or in terms of algebraic equations, stochastic equations, various models one can have, even mathematical model itself. If the attributes, if one attribute in mathematical terms, we say the dependent variable of one entity in the system, if that's going to vary with respect to another attribute, okay, so one variable is changing with respect to another variable in mathematical terminology or system terminology, or an attribute of of one entity is changing with respect to another attribute of another entity, and then we say that there's a rate of change of this rate of change can be quantified. Rate of change of one variable with respect to another variable, that can be quantified, thanks to Newton and Leibniz. They came up with an idea of how to quantify the rate of change of a function or a variable with respect to another variable in terms of the derivatives. So if there's a change in the system, variable with respect to another variable within the system, then we can model the system in terms of a derivative involved. That is called a differential equation, a mathematical model involving derivatives of the dependent variables results in differential equation. That if you have more number of independent variables, then you may have a partial differential equation. If there's a single independent variable, then it may result in ordinary differential equation. So we now in my talk I deal with the ordinary differential equation for a satellite model. Okay, so coming to my problem, a satellite control problem. Suppose that we have a satellite which is orbiting about the Earth, along a prescribed orbit. Okay, and how to model that system, how to represent the dynamics of the system. Dynamics of the system means you should have the knowledge of the position of the satellite at any time, and also the velocity of the satellite, position of the satellite, and various other aspects of the satellite at any time. Those are the state variables, and you want to make a model describing the complete state, complete description of the satellite at any time, at any given time. So that's what we do in the model. So for that, consider the situation, a satellite of mass m. So consider a satellite of mass m orbiting around the Earth under the inverse square law of field. So we assume that satellite has got two thrust states. This red dot indicates a satellite, and the center of the circle is Earth. And this satellite is having two types of thrust states or controls. Okay, along the radial direction, along our direction, we assume there's a radial thrust U1, and along the transverse direction or the tangential direction, we have U2 as a control. So for a satellite with the two types of controllers, the radial controllers, radial thrusters, and the tangential thrusters, which moves around the Earth, and we want to model the dynamics of this satellite in terms of differential equation, in terms of mathematical equation, that is in terms of ordinary differential equations, system of ordinary differential equations. Okay, so coming to the modeling part, if P is the position of the mass, and in Cartesian coordinate xy, if xy is the position of the satellite, okay, P at any time t, okay, in the rectangular coordinate, then the equation of motion is given by Newton's second law of motion. Mass into acceleration is a force. M into x double dot. X, okay, it's a movement is position in the direction of x is denoted by x. X of t. X is a function of time. So mass into x double dot, which is mass into acceleration in the direction of x, which is equal to the force applied in the direction of x. Okay, And similarly, along the direction of y, m into y double dot is f of y. Okay, so that fy is a force component in the direction of y-axis. Okay, and this is in Cartesian form, but it is convenient to use the polar coordinate system here because r and theta, because it revolves around the earth, and r and theta, the angular position, angular velocity, and the radial distance, those are important and easy to calculate and visualize. Also, therefore, we convert this mathematical form in terms of the polar coordinate system, taking r and theta as the variables. So we know the transformation x is equal to r cos theta and y is equal to r sin theta is the conversion formula for the from x the Cartesian to the polar. Okay, so let's do this transformation and change this equation. Okay, so the equation of motion in polar coordinates. Okay, consider the object or the satellite is at the position P, and if you resolve the component of velocity of the particle in v direction and the u direction, let u and v denote the component of velocity of the particle along the radial direction r and along the tangential of the transverse direction. Okay, so u and v are the velocity component in the radial and transverse direction. Then the resultant of u and v is also same as the resultant in terms of the Cartesian coordinate system, x dot and y dot. So therefore, by resolving this velocity in the direction of x, we can if theta is angle, r is radial movement, radial direction, and theta is the angle the satellite is making with the x-axis. Then x dot, you can resolve the velocity in the direction of x and also in the direction of y. So x dot you get as by using the theta is a u cos theta minus v sin theta is a velocity component in the direction of x. Okay, and similarly, okay, so that is x dot is equal to u cos theta minus v sin theta. And the transformation formula we have x is equal to r cos theta. If you differentiate this with respect to t, you can also compute x dot. So if you differentiate x is equal to r cos theta with respect to time, this is x dot is equal to r dot cos theta minus derivative of cos theta is sin theta, r sin theta into theta dot. And these two must be same. So from equation 3 and 4, you can equate these two. U cos theta minus v sin theta is same as r dot cos theta minus r sin theta, theta dot. And comparing the coefficients of cos theta and sin theta, now from equation 5, we get the formula u is equal to r dot and v is equal to theta dot. So that means u is equal to r dot is at radial velocity of p, and v is equal to r theta dot is a transverse component of the velocity. So therefore we got in terms of the velocity in terms of the polar coordinates. Okay, now we will find the same thing for acceleration. If we assume that a1 and a2 are the components of acceleration in the direction of radial and the transverse directions, then again resolving in the same way along the direction of the x-axis and the y-axis, x double dot is a1 cos theta minus a2 sin theta, and again differentiating the previous equation 4, which we got from the transformation equation. X dot, if you differentiate in one more time with respect to t, you got the acceleration. So that x double dot is dx dot by dt. Okay, you can differentiate it, and it results in this form. So r double dot minus r theta dot square cos theta minus 2 r dot theta dot plus r theta double dot sin theta. Again, so now you can compare this again with along with the previous equation. So equating the value of x dot in these two systems, then we get a1 cos theta minus a2 sin theta is r double dot minus r theta dot square cos theta minus 2 theta 2 r dot theta dot plus r theta double dot sin theta. So now you compare the coefficients of cosine theta and sine theta, and you get the acceleration. Okay, so comparing the coefficient of cosine theta and sine theta, we get a1 is equal to r double dot minus r theta dot square, and a2 is 1 by r d by dt of r square theta dot. For convenience, we write that way. Okay, we compact 4. So the 4 are the quantities a1 and a2 are for the radial and transverse component of the acceleration. Now going back to Newton's law, okay, our first equation of motion of the particle P can be written as mass into acceleration is the external force. Okay, mass is m into acceleration in polar coordinate is r double dot minus r theta dot square is a force. Okay, in the direction of the radial direction fr, and in the transverse direction, mass into the acceleration we just now found. The acceleration is a2. Okay, so a2, if you use that a2 value, then it is 1 by r into d by dt of r square theta dots. Okay, which is equal to ft. So the two equations are ready. Okay, so equation of motion in polar coordinates. So in the case of central orbit, the force, we know that for a central orbit, the force is always directed towards a fixed point, okay, the center. If we take this point as origin, then, okay, of course, this f theta becomes 0, and that balance and its f theta is 0. And if fr is equal to, by using the inverse square law, okay, inverse square field, you have the external force as k minus k upon r square. Okay, that's k is a constant. The inverse square law is applied here, and the force is always in the direction opposite to the pulling direction. So therefore, we have the two equations. M r double dot minus r theta dot square is equal to minus k by r square, and m r theta double dot plus 2 r dot theta dot m is equal to 0. So we got two equations. Okay, these are the two mathematical equations describing the motion of the satellite. Okay, about an orbit. Okay, where theta is the angle and r is the radial direction, the radial position. So okay, now assume that the mass is equipped with the ability to exert. Now we assume that the satellite has got two thrusters, two controllers. Okay, the mass is equipped with two forces, thrust u1 in the radial direction and u2 in the tangential direction. Okay, so therefore you can add in the first equation u1. Okay, that is for the for the radial direction, and second equation for the transverse direction you can add u2. So therefore you get a controlled system. So the previous system was uncontrolled. I mean uncontrolled in the sense there was no control term coming. That was from the just the dynamics without any thrusters or any controller. And here this equation number 9, m r double dot minus mr theta dot square plus k by r square is equal to u1. U1 is a thruster in the tangential in the radial direction, and 2 m r dot theta dot plus r theta double dot m is equal to u2, where u2 is a tangential thruster. So this coupled equation gives the dynamics of the satellite at any time t. Now we want to study further properties. We want to find the solution. We want to study the control property of this system. So the controllability, we will mainly study about the controllability of the system. I will define what is controllability. Now these coupled equations. So look at these equations. These equations are totally non-linear ordinary differential equations. and we will put them into state space form first. Okay, state space representation of the equation. So assuming that without loss of generality, we assume that the mass of the satellite is 1, just to now for the sake of simplicity, okay, to make it convenient, assume that the mass of the satellite is 1, then the motion of the satellite is described by a pair of second order differential equation, d square r by d t square is equal to r into, okay, d theta by dt square minus k by r square t plus u1, okay, first equation. And second equation is d square theta by dt square is equal to minus 2 by rt into d theta dt into dr dt plus ut by rt. Okay, this is a general equation. Okay, two second order equations, nonlinear equations with the two thrust states u1 and u2. And we will take a special case. Suppose that there is no thruster. u1 and u2 both are 0. Okay, there is no tangential or radial thruster. Then one can easily solve this equation and show that rt is equal to sigma for some constant and theta t is equal to omega t. Okay, this is a solution to the given equation. Okay, where sigma and omega are constant, and one can find that these constants are related by a relation sigma cube omega square is equal to k. Okay, so therefore, so we have for an uncontrolled system, this is the solution. What is the solution? Rt is equal to sigma. Sigma is a constant. Means it is taking a circular path. Rt at any time t, it is a constant. Means the satellite is taking a circular path, and the theta t is angular position is omega into t. So omega into t is and therefore its angular velocity is omega. Angular velocity is omega. So therefore its position and angular velocity, okay, are the solution of these coupled nonlinear equation. And this is solved for a very special case. If there's no thrust states, then this is one of the solutions. Now we have two equations, two nonlinear equations, and both are second order equations. We can reduce this second order equation into first order equations. So if you reduce this two second order equations into first order equations, we get four equations, four first order equations. Those four equations are known as a state space representation. Okay, so for that we have to change, make a change of variables. So let's call x1 is r minus sigma, and x2 is its velocity, its derivative. Okay, and x3 is sigma into theta minus omega t, and x4 is its velocity. Okay, x4 is x3 dot, and x2 is x1 dot. So that's the usual way how we convert a higher order differential equation into first order system of equations. So this gives now we can from this expression r is x1 plus sigma, and r dot is x2, and theta is x3 by sigma plus omega t, and theta dot is x4 by sigma plus omega. So this, if I make use of these four variables, now I defined these four state variables. Okay, x1 is to do with something to do with the radial position, and x2 is a radial velocity, and x3 has to do with its angular position. x4 is angular velocity. It's related to that. So four components, four state variables I define. Then in terms of these four variables, my equation can be written as, so using the above transformation, our two second order and nonlinear equation reduce into a system of four first order equations, four first order nonlinear equation. dx1 by dt is x2, and dx2 by dt is okay, that is coming from the first equation. This okay, and here you have the controller u1, and dx3 by dt is x4, and dx4 by dt is coming from the second equation, where the u2, okay, the thruster is also inverted. So these are the four first order equations representing the dynamics of the artificial satellite. Okay, now we will write this into a compact form. The above equations form a system of nonlinear ordinary differential equations involving forcing terms, controller U1 and U2. So this can be written in a very compact form where we define f as a function. Okay, so the state variable xt is having 4 components: x1, x2, x3, x4. So therefore xt is in R4. And the control ut is having 2 controllers, the tangential and the radial thrusters U1 and U2, which is in R2. And f is the right hand side of the above equation, which we have seen. This the right hand side of this equation. This is my f. Okay, so if I take this convention, then f1 in f is having 4 components. F1 is a function of x1, x2, x3, x4, the state variables, and control U1 and U2 is x2. F2 similarly is given by this, F3 is x4, and F4 is given by this expression. Okay, so therefore, this is a compact form of a nonlinear differential equation in higher dimension. Okay, vector differential equation. Okay, now since it's a nonlinear, to get its solution is not that very easy. What usually we do is we will linearize this nonlinear equation. For a practical point of view, you want to linearize this equation and then make a get a linear system, then study the property of the system. That's what a practical point of view we do. So linearization of the nonlinear system. So we now linearize the nonlinear system about the zero equilibrium solution. We have seen that when there is no controller, U1 and U2 0, then we already obtained one solution. One solution we obtained was this one: RT is equal to sigma and theta t is equal to omega t. Okay, if we linearize the system about this solution, okay, so if we it becomes RT minus sigma, that becomes 0, and theta t minus omega t, that also becomes 0 by definition. So the origin is nothing but the origin in the new system is going to be my earlier solution. Okay, solution in the previous simple case when there's no control. So therefore, we linearize the system about the zero equilibrium solution. Zero equilibrium solution is the solution we obtain for the same system when there is no controller, U1 and U2, okay, both are 0. So this linearization is done by using the Jacobian linearization. You take the Jacobian of the the function with respect to the state variable. Okay, so if you linearize it, you get a very handy linear system. Okay, this is a linear system. X dot is equal to ax plus bu. Okay, where A is a matrix. That matrix is given by the Jacobian. Okay, del f1 by del x1, del f1 by del x2 up to del f1 by del x4, and similarly up to the 4th component, and evaluate at the given solution. Given solution is 0, 0. The equilibrium solution is a solution which we already obtained. So then I get a constant 4 by 4 matrix. I get a 4 by 4 matrix. If I evaluate this the partial derivatives at 0, 0, I get a matrix, constant matrix. And similarly, B is also the same function f. If I take the Jacobian with respect to the controller U1 and U2, I get B. And with respect to the state variable x1, x2 up to x4, I get A. So therefore, both the matrices A and B are obtained by linearizing the nonlinear system. So B, okay, so if you do that, you get A is equal to 0, 1, 0, 0, 3 omega square 0, 0, 2 omega, and 0, 0, 0, 1, and 0 minus 2 omega 0, 0 as my A matrix. And B is the Jacobian with respect to the control variable, okay, U1 and U2. So you find the partial derivative of all the F4 components, F1, F2, F3, F4, and you get a matrix B. So this is my B matrix, okay, and evaluate at the given solution. So, and here sigma is normalized to 1. You can normalize sigma to be 1, and the linearized control system takes the form x dot is equal to AX plus BU. Now we study the control property of this system. So therefore, we got a system of the form X dot is equal to, okay, AX plus BU, okay, which is a four-dimensional. So where X is in R4, okay, X is in R4 and U is in R2. So therefore, we obtained a vector differential equation, okay, representing the motion or the dynamics of the satellite. We study the control aspect of it. Okay, to study that, we take even a slightly a general system. Now, after linearization, we got a matrix A, which is a constant matrix, and B is also a constant matrix. That need not be the situation even if A and B are time-dependent matrices. Still, my theory will work. So therefore, I take a more general case, and I will state the theory. Then I will specialize to the particular example of the satellite. Okay. Now it's the general theory. So consider a linear control system represented by the equation dx by dt, which is equal to atxt plus btut, where t is a time interval. The time interval of interest is a t0 to t1. So t0 could be 0 and t1 is maybe some hours or maybe for months or years together. So that is a time interval, and except t0 is x0. Okay, that's the initial state. So where x0, xt, they are in Rn. So in my satellite problem, n was 4, but now I am taking a more general system. So I am having a system, n-dimensional system, where I have n state variables, and I have controllers. This ut is in Rm. So they are functions. So I assume that they are square integrable functions, L2 functions, Levy square integral functions, L2 functions. Okay, that's more general than the continuous functions, in which step functions or your piecewise continuous functions are all included, for a practical point of view. So where AT and BT are matrices of dimension n by n and n by m, and assume that the elements of the matrix AIKT of AT are absolutely integrable functions. Okay, you can take their continuous or even integrable. Okay, more weakly, and the elements Bij's of BT, they are assumed to be piecewise continuous functions of time. Okay, so AT BT are matrices having its entries at least piecewise continuous or integrable functions. Okay, that is the assumption. Now we are going to get the solution of this system. It's a general system, nothing to do with the satellite. It's a general control system, mathematical equation. It is a mathematician's terminology. It's a non-homogeneous linear vector differential equation. Okay, so BTUT is a forcing term, or what you call the non-homogeneous term, and AT is a part of the equation. Dx by dt, first order linear equation with a non-homogeneous term with an initial condition. Is an initial value problem of a non-homogeneous system. So we want to find the solution of the system. Okay, let me go. Okay, now first I define what is a controllability of the system. That is relevant to satellite problem also. Controllability means I say that the system is controllable if from an initial state, controllable or a time period, say is a time period is t0 to t1 is an interval in which I am interested. So at t0, my position is here at x0. Okay, and if I want to steer my system, okay, if I want to take my system to another position, say at t1, if I want to bring it at t1, it should come here. Okay, so therefore I have to steer it along a direction, along a path, and it comes here. So from x0 to x1. So therefore I have x0 in Rn and x1 is also in Rn. Okay, I have two states, arbitrary states in Rn, and my question is, does there exist a controller Okay, my control system is this. Does there exist a controller UT such that once I plug in this UT, my initial state, okay, X0, my initial state X0 can be steered to X1 at a time T, okay, T1, okay, at the final time T1. If that happens, so if such a controller exists, then we say that the system is controllable. A system is controllable on an interval T0, T1 if for every pair of vectors X0, X1 in Rn, there is a controller UT in L2. Okay, this L2 is, okay, L2, T0, T1 in Rn, such that the solution of the system satisfying the initial condition except T0 is X0 also satisfies the desired final condition except T1 is X1. So once I start from X0, it should move to X1. Okay, I start from X0 at T0 and it is now ending up at X1 at T1. If this happens with a suitable U, then I say that my system is controllable. Okay, so therefore, the controllability concept is a common concept. It comes in many of the systems. Okay, if you see a enemy's warplane is coming over the country, okay, a plane is coming and you have a missile on the ground and you know the position of the missile, and at time T is equal to T0, the position of the missile is on the ground at your station, and you calculate the position of the enemy's the plane at a specific point in space, and can you give a command to the missile so that exactly at that time, say 10 minutes, in 10 minutes or 5 minutes, my missile is hitting the warplane exactly at that point, so that it may smash that flight. If that is possible, then I say that, okay, the situation is under controllable. So this is controllable. So a system is said to be controllable if any arbitrary initial state can be steered to a final desired state in a given interval by using a suitable controller. If that happens, the system is controllable. I mean, it applies to human, physiological body, human body. Say the sugar level, the morning is found to be 300 or 400, a blood sugar, and it's too much, and you want to control it. Okay, within a week, the time period could be a week, and the doctors advise the drugs or insulin. Okay, you take 2 times or 3 times or 1 time, so that within this time, by applying these controllers as medicine or drugs, it brings it down to a normal 100 or less than 100. So that's controllability is applied. You just name any field, all these fields, controllability aspect is coming. So you want to steer the state of the system from an initial given state to a given desired final state. So that is a controllability. In a satellite problem, what is controllability? Satellite, we launch satellite, we inject these payload satellites at certain orbits so that it may do somewhat. Maybe it is capturing the images. It is capturing the images of our land, and it is transmitting to us. So therefore, there's some orientation of the camera of the satellite we desire. But because of some reason, some cosmic reason, some forces, the orientation may slightly tilt. Okay, the satellite may slightly move away from the desired orientation. So you want to bring it back so that we get the right data. So instead of photographing, instead of taking the image of Indian territory, if it's going to take images of another neighbor's territory, that's dangerous. That's not cool. It's cannot be allowed. So therefore, it has to be corrected immediately. So there are thrusters already built in a satellite. That thrusters can be fired. By firing those U1 and U2, it will bring it back to the desired orientation. Okay, so those are the controllers. So for a given given initial state to a desired final state, can you apply some kind of controllers so that it does the job, or it is doing the steering? That is a mathematical idea of controllability which is applied in physical systems. Okay, coming to now, okay, we will address these questions. We will find a characterization for a system to be controllable, a necessary and sufficient condition for a system to be controllable, is derived or is established by a famous mathematician, engineer, Ari Kalman. It was developed in 1960s, and a complete characterization was given by Kalman. Later, subsequently, it was again generalized to various, advanced systems. And it can be applied to a given practical problem. Okay, to do so, we will first address the solution to discuss about the controllability or the controllability aspect. We will first find a solution, mathematical solution of this equation 15. This is a linear system. Since it is linear, everything is clear and everything is well known, it's already developed. So to define a solution or derive a solution of the linear problem, I define what is known as a transition matrix, and by that I define the solution of the system. Okay, so to define the transition matrix, what I do is the transition matrix of the linear problem, I take a uncontrolled, without non-homogeneous part. X naught is equal to ATX. I have X naught is equal to ATX, and the initial condition is an initial value problem without forcing time, without non-homogeneous state. And where AT is a matrix and by n matrix, and whose entries are assumed to be continuous or piecewise continuous, then we know that from the fundamental existence and uniqueness theorem in ordinary differential equation theory, that this system has a unique solution, a linear problem with an initial condition, and if the component, the matrix is continuous with respect to t, then it has a unique solution for any given x0. Now, if the solution is, the initial condition is not given, okay, how many solutions are there? For a given initial condition, it has a unique solution. But if you take all other possible solutions, okay, without initial conditions, we can show that the set of all solutions of this system forms a vector space of dimension n. So the solution space is a finite-dimensional space of dimension n. That means the basis will have n elements and functions that can create, that can span any solution in the solution space. A set of n linearly independent initial states in Rn will provide a set of n linearly independent solutions of the set of. Okay, that is one one very interesting observation, that if I take x0 fixed, then with respect to x0, I have a unique solution. And now x0 is an Rn. Now, if I take n linearly independent vectors in Rn and find the corresponding unique solutions, then those solutions will be linearly independent solutions. And those solutions can span the solution space. So therefore, the basis for a set of all solutions of this x naught is equal to axt can be found by taking the linearly independent solutions of this equation. That can, in fact, practically taken from the linearly independent vectors in Rn. Okay, so I just state the fundamental matrix solution, which is the fundamental matrix solution theory is taught in the MSc level in mathematics. Set of all solutions of the linear homogeneous system 16 forms an n-dimensional vector space over the field of real numbers. That is a theorem. And n by n matrix function phi t. If I define a matrix function phi t, in which each column is a linearly independent solution of your linear system. Okay, so n by n matrix matrix function said to be a fundamental matrix. Such a matrix is called a fundamental matrix. Is said to be a fundamental matrix solution of the homogeneous system if n columns of phi are linearly independent solutions of 16. That's the linear system. So the linear system has n linearly independent solutions because in Rn there are n linearly independent vectors. those n linearly independent vectors will give rise to n linearly independent solutions. If you put all those n linearly independent solutions in a matrix, that matrix is nothing but a fundamental matrix solution. So therefore, how many fundamental matrix solutions? There are infinitely many fundamental matrix solutions, because in Rn there are so many sets of linearly independent vectors in Rn. For each such linearly independent vectors in Rn, you can find the corresponding linearly independent solutions in the solution space and put them in a matrix. That becomes a fundamental matrix solution. And so therefore, the linear system has any number of fundamental matrix solutions. And a very special fundamental matrix solution is known as a transition matrix. That's what we define. So evidently, phi satisfies. If phi is a n by n matrix whose columns are linearly independent solutions, then d by dt of phi t is equal to at phi t. We can easily prove, because each entry is a solution. If you differentiate each column, one a will come out, and at into phi t will come out, and that you can take outside, and this matrix satisfies the differential equation, and is a matrix differential equation. Okay, this becomes a matrix differential equation. Okay, now note that any solution of 17 need not be a fundamental matrix solution. So now if I take a solution of this matrix differential equation, a solution of this matrix differential equation is going to be a fundamental matrix solution, but only those solutions having linearly independent columns are known as a fundamental matrix solution. So one note is that any solution of this one need not be a fundamental matrix solution, but those solutions which are linearly independent, are known as a fundamental matrix solution. Okay, so due to lack of time, let me just go quickly. So therefore, fundamental matrix solution, if phi t is a fundamental matrix solution of the linear system, and C is any constant non-singular matrix, then the product phi t into C is also a fundamental matrix solution. If phi t is a fundamental matrix solution and C is another constant matrix, compatible for multiplication n by n matrix, then the product, if you oppose to multiply phi t by C, then phi t C is also a fundamental matrix solution. But note is that if you pre-multiply, then there's no guarantee that C into phi t need not be a fundamental matrix solution. Okay, so the proof explanation, I'm not going into it. And now I come to the definition of a transition matrix. If phi t is a fundamental matrix solution of the linear system, and if I evaluate that matrix, because that matrix is consisting of all functions, all solutions, and evaluate that solution at any point t0, then that's going to be a constant matrix, constant n by n matrix. That matrix will be a non-singular matrix, because these solutions are linearly independent solutions. And if I evaluate the solution at any time point, and I form this vectors into a matrix, that matrix will be a non-singular matrix or invertible matrix. So if I fix t0, the initial time t0, then that will be an invertible matrix. If I call that matrix as C, C inverse is my, okay, phi t0 inverse is my C. Then my previous proposition, phi t into C is, okay, that is phi t into phi inverse t0, which is also a fundamental matrix solution. And this fundamental matrix solution is known as a transition matrix, okay, and is denoted by phi t t0. Phi t t0 is nothing but phi t into phi inverse t0. Okay, phi t is a n by n matrix, phi inverse t0 is also a n by n constant matrix, and this product is an n by n matrix. This is also a fundamental matrix solution of the linear system, and this is known as the transition matrix. And some of the properties of the transition matrix, okay, why it is called a transition matrix, I will explain later. Phi tt is always, if both the arguments are same, it's going to give you a semi-group property, phi t tau into phi tau t0, okay, and phi t tau okay, is also same as phi t into phi tau inverse. That's from the definition itself. Okay, so these are some of the properties of the transition matrix. And the transition matrix can be computed, from the given matrix A. So a sequence of matrices Mk recursively defined by M0 is identity. Mk is I plus integral T0 to T, A to Mk minus 1. Okay, if I recursively define this matrices, then this sequence of matrices converges uniformly in the interval T0, T1. And if the limit function is denoted by phi t T0, then that limit function satisfies your differential equation, given equation, d by dt, phi t T0 is at into phi t T0, and its value at T0 is identity. It is satisfying the, the property of the fundamental matrix solution. And therefore, the solution of 15, which passes through x0 at t is equal to T0, is given by the solution of the solution of the non-homogeneous equation. Once you have the transition matrix and this equation, by variation of parameter method, you can show that the solution of the non-homogeneous equation is written in terms of the transition matrix which we just defined. The transition matrix can be computed by this iterative scheme, recursive scheme. Xt is equal to phi t T0 x0 plus integral T0 to T phi t tau v tau u. Okay, and again the solution, representation of the solution, how to get this transition matrix. Okay, the transition matrix from the above lemma, if you expand it, if you recursively write those integral, then phi t T0 takes this form, this infinite series form is known as Peano-Becker series. So Peano-Becker series identity plus T0 T, 8 tau and d tau plus then 2 integral, iterated integration, then 3 integral and so on. And this is an infinite series that converges uniformly in the interval, and that is your transition matrix. Okay, a very special case, if A is a constant matrix, then if A is a constant matrix, then the Peano-Becker series becomes matrix exponential, I plus A into T minus T0, because A is a constant matrix here. So integral of that is A into T minus T0. And similarly, you have 2 times integration, that is A square, A, both A, this A and A are constant, A square into this iterator integral, T minus T0 square, okay, this square by 2 factorial, plus etc. So you get this one. This is nothing but e to the power A T minus T0. It's a matrix exponential. So using the variation of parameter formula, the solution of the non-homogeneous equation can be shown that, okay, the solution of x dot is equal to ax plus bu with the x at T0 is x0 is given by this integral representation. Okay, this is a solution, explicit solution for, right hand side everything is known, solution of the non-homogeneous equation. Okay, fine. So now, okay, there are many ways you can define transition matrix. Okay, due to lack of time, let me just skip this, the transition matrix computation here. This I will skip. Okay. There are actually there are so many methods for the computation of the exponential of a matrix. For example, if A is diagonalizable, if the matrix A is diagonalizable, then computation of exponential of AT is easy. Okay, then A can be written as P into D into P inverse. Okay, with the eigenvectors of A and the eigenvalues are the diagonal entries of D. Then e to the power AT is given by this. E to the power AT can be written as P into P is a matrix coming from the eigenvectors of A, and e to the power dt. E to the power dt is D is a diagonal matrix. So therefore e to the power dt is just the exponential of the diagonal entries. So therefore this is clear. Computationally it is given. It is known. Now the case if A is not diagonalizable, but we know that A can be written in the Jordan decomposition form. In that case also, if A can be written in the Jordan form, then also there are expressions without going into much details. I will say by using the eigenvectors and the generalized eigenvectors. Using the generalized eigenvectors, you can span the entire complex Cn with the eigenspaces of the matrix. Okay, with each eigenvalues. Okay, then also e to the power at x0 can be written as a summation form. Okay, and computing transition matrix, in that case, transition matrix will be of this form. Okay, so it is having different eigenvalues, lambda 1, lambda 2, etc., lambda n, but it is having some of the eigenvalues are complex, some are real, and the eigenvectors are not fully matching with the dimension of your space. Then take care of the situation with the generalized eigenvectors. Still, you will be able to write the matrix exponential. Okay, one example is given here. If x0 is equal to x, A is a simple 2 by 2 matrix. Eigenvalues lambda 1 is equal to -1, lambda 2 is equal to 2, and eigenvectors of A are 1, 0 and -1, 1. Then corresponding to these two eigenvalues, -1 and -2. Then A can be written as A is equal to PD into P inverse, where P and D are given by the following matrices. Okay, P is a diagonal, P is eigenvectors, and D is the diagonal matrix having the eigenvalues. Then exponential AT is P into e to the power dt into P inverse, which is given by this expression. And finally, the transition matrix e to the power AT is computed. Okay, in this manner. Okay. Now, okay, in case it's not diagonalizable, in the previous example, it was diagonalizable. You had two eigenvalues distinct, and you had two linearly independent eigenvectors. But if the eigenvectors are not going to span the entire Cn, then you not make use of the generalized eigenvectors. Okay, then also, a theorem says if A is an n by n matrix with the eigenvalues lambda 1, lambda 2, lambda n repeated according to their multiplicities, and then there exists a basis of generalized eigenvectors. Okay, these are the generalized eigenvectors with the matrix formed by generalized eigenvectors is P. Then A is S plus n, where P inverse SP is diagonal of these eigenvalues. Then a matrix N is defined as A minus S, is a nilpotent matrix of order K, which is of course less than or equal to N. Okay, and S and N commute. Then phi T0 can be written in this form. Okay, okay. Those of you who are interested, you can just refer to this Perkos book on differential equations and dynamical systems. So you can get the transition matrix even for the case where all eigenvalues, the matrix is not diagonalizable and the eigenvectors are not complete. Okay, now we come back to the linear system. Okay, so we are back with the system x dot is equal to ax plus b ut, and the solution is written by using the transition matrix xt is equal to phi t0 x0 plus integral t0 to t phi t tau b u tau d2. This is the solution of this system. Okay, solution of this system by using the transition matrix. Again, okay, I didn't tell you why it's called transition matrix. Okay, so transition matrix, because if I know the linear system x dot is equal to atx, and if I know the value of the solution at t0 is x0, okay, then the solution of this system, okay, linear system is given by phi t comma t0 into x0. It means from any initial state x0, it gives you the future state, okay, xt, t greater than t0. So it gives you the transition of the state of the system. So transition matrix, if once you multiply the transition matrix by a given initial state, it gives you the future state. So therefore, we call this matrix as a transition matrix. Okay. So now the controllability problem, which I have already defined what is controllability. The dynamical system x dot is equal to axt plus but with the initial condition x at t0 is x0 is said to be controllable during a time interval t0, t1 if for every x0, x1 in Rn, there exists a controller u, okay, there exists a controller u such that the corresponding solution starting from the given initial state also satisfies the desired, okay, final state x at t1 is x1. That is the controllability. Okay, in our system, we are going to characterize, how to characterize the controllability. Okay, so therefore, the system x dot is equal to x plus bu with the initial condition x at t0 is x0, x at t0 is x0. We are looking for a controller u, because we are looking for a controller u, which will steer the system to x1 during the interval t0, t1. Okay, so that is corresponding to that solution. Now it should satisfy the desired final state. So we are looking for a u such that x at t1 is x1. Okay, and the solution is what? Solution is phi at t1 t0 x0 plus integral t0 to t1. Okay, I'm fixing t. Okay, when I fix t with a t1, integral t0 to t1 phi t1 t vt ut, and this should be equal to x1 for a particular u. I am looking for this u. This is unknown to me. Can I find a u once I plug in that u into this solution? Okay, my terminal state x at t1 is okay, x1. That's the question. That means if you take these terms to the left hand side, x1 minus phi t1 t0 x0 is integral t0 to t1, and the right hand side is just the integral phi t1 t bt ut. So I am looking for a u such that this is satisfied. So now coming to the functional analysis, you define an operator. So u is a controller. Define an operator C which is mapping my L2 space to Rn. Rn is a state space. Left hand side is in Rn. Is in Rn. Okay. X1 is in Rn. Phi T1, T0, X0 is also in Rn. Okay. It's a vector space. Okay. The difference is also in Rn. So I'm looking for a control function U, which is in L2, which maps, okay, to Rn. And the operator defined by integral, the right hand side, integral T0 to T1, phi T1 tau, B tau, okay, B tau, okay, U tau. B tau, D tau is Cu, and that should be equal to your, if I denote the left hand side by omega, this should be equal to omega. So I'm looking for a U. I don't know whether there exists. I'm looking for a U such that for every omega given, okay, I can find a U satisfying this equation. So obviously this integral operator is a linear operator, and you can show that they are all matrices. Okay, and so therefore it's a bounded linear operator. So therefore, if I denote, okay, the left hand side I denote by D. So D is equal to x1 minus phi t1 t0 x0. Now the equation, okay, the equation above that becomes Cu is equal to D. That means for a given, so what we are looking for a given D, can I find a U such that Cu is equal to D? So what is this problem? This is some kind of solvability. Okay. So if for any arbitrary D, if there exists a U in L2 such that C is equal to D, then my system is controllable. That means if C is onto, then the system is controllable. So therefore, mathematically, controllability is nothing but the onto-ness of the bounded linear operator C. And if C is onto, again, if you take the adjoint of this operator, okay, if I define C is from L2 to Rn, and the operator is defined by Cu is equal to integral T0 to T1 to this, okay, integral operator. It's clear that the system is controllable if and only if the operator C is onto, or C transpose. Transpose is the adjoint. From Rn to L2, B, it's adjoint. Then you can show that the expression for adjoint, by taking this inner product, you can get the adjoint of C is given by B transpose T into phi transpose T1 T. Okay, this is adjoint. So if C is onto if and only if C transpose is 1, 1. Okay, so adjoint is 1, 1. So if okay, CT denotes adjoint of C. C is onto if and only if CT is 1, 1. And that also equivalent to say that CCT. Okay, CCT will be from Rn to Rn now. Rn to Rn is positive definite. That's a matrix. The operator C transpose is known as a controllability Grammar, and which is okay given by this expression, because this portion is C and this portion is C transpose. Okay, this is C transpose is W, and this is obviously C transpose is from Rn to L2, and C is from L2 to Rn. So therefore, C transpose is from Rn to Rn, Rn to Rn. So therefore, it's a bounded linear operator from Rn to Rn. It has to be a matrix. It has a matrix representation. So therefore, that matrix is known as a controllability grammar. So Kalman has established the result that the linear system is controllable if and only if this matrix is invertible. Okay, C transpose is positive definite means invertible. Okay, so therefore, and also we can show that if that matrix is invertible, W inverse exists, and if you define a controller by this B transpose, phi transpose, W inverse, okay, times x1 minus phi, T1, T0, x0, this is a controller which is steering, okay, my initial state x0 to a final state x1 during the time interval t0 to t1. So this controller, this is a controller which is steering the any initial arbitrary state x0 to a desired final state x1 in the time interval t0 t1. So therefore, if a controllability grammar is known to be invertible, then you know the controller, steering controller is also ready. Okay, in fact, you will see that this controller is not only just a controller, it is a controller having a property that out of all possible such steering controllers, this is a controller which is having the minimum energy, minimum L2 norm. This is a minimum norm controller, minimum energy controller. Okay, so I state the controllability theorem. The following conditions are equivalent. The system is controllable if and only if C is onto, if and only if C star is onto, or that's also 1, 1. It's a n-by-n matrix. Onto means 1, 1. So C star, CCT is called a controllability grammar, is given by this, which we have seen. So therefore, you can also view in a different way. We are looking for the solvability of C is equal to D. D contains x0 and x1. And we are looking for the solvability of C. For every D, there should be a U. Okay, so C should be onto. And if I want to solve it, I can also solve, instead of solving Cu is equal to D, I'm going to solve C transpose V is equal to D. If a C transpose is invertible, okay, if C transpose is invertible, then I can find V. Once V is known, then the U is given by C transpose V. Okay, so V is C transpose inverse times D. So therefore, the steering controller is given by C transpose inverse D. In fact, this is nothing but the generalized inverse, Moore controls inverse. Now we call, controls got the Nobel Prize in physics this year. The same controls had, and his student Moore introduced this generalized inverse, Moore controls inverse, and this is a Moore controls inverse. If Cu is equal to D is the equation, and if you want to solve for U, but you know that C is not invertible, but you look for a generalized inverse, that inverse is your C dagger, D, which is a generalized inverse, Moore controls inverse, in terms of a matrix. Okay, and once that inverse is known, which is least, in fact, it's a least square solution of the equation. So therefore, if the system components, matrices are constant matrices. All my discussion so far is true, even valid for a time varying matrices. AT and BT can be time varying. Okay, so for time varying matrix also, the above theorems, the results are true. But in case if the matrices are time invariant, LTI matrix, linear time invariant system, okay, then we have even much simpler conditions, is also known as Kalman's rank condition. If my system is x dot is equal to ax plus bu, A is a constant matrix, B is also a constant matrix. Then if the rank of B, AB, A square B up to A n minus 1 B is n, this matrix is called a controllability matrix. And if this rank is n, then the system is controlled. It's a necessary and sufficient condition. Okay, and also no eigenvector of A transpose is in the kernel of B transpose. That's another equivalent condition for controllability. Or eigenvalues of A plus BK can be placed arbitrarily for some suitable choice of K. This is equivalent to the stabilizability. Okay, so it is expressed in terms of stabilizability, or the rank of A minus lambda I B for every lambda being an eigenvalue of A. If this rank is n, then also the system is controlled. Under any one of these equivalent condition, the LTI system, linear time invariant system, is controlled. Okay, and the advantage of the controllability grammar is there you can also compute the control, and the steering controller is given by this expression. Okay, we have the steering controller is ready in that case. Okay, now okay, fine. So this is a verification how to show that this, if this is a control, ut is a given control. If you plug into the system, it satisfies both at t is equal to t1. If you evaluate it, you can show that at t is equal to t1, the value of the state is x1. Okay, and so let's come back to, I have, I think 5 minutes more, right? Okay, so I come back to the satellite problem. So our satellite problem is a 4-dimensional problem. So dx by dt is equal to axt plus but, where A is this 4x4 matrix and B is this matrix. Okay, having two components in the controller U1 and U2, the radial and the tangential thrust states. Okay, this is our original satellite problem, linearized problem. Okay, now to compute the transition matrix for the satellite problem, okay, if you find the eigenvalues of A, okay, the eigenvalues of A are 0, 0 is a repeated root, and plus omega I and minus omega I, they are the complex conjugate roots. Okay, so it has got the 4 roots, and the procedure of eigenvector method. So you can find the eigenvectors corresponding to lambda is equal to 0. 0 is a repeated eigen value. Corresponding to 0, we have these two eigenvectors. Okay, and also corresponding to the complex eigenvalue plus or minus I omega, we have these two two eigenvectors here. Okay, so therefore the P matrix in the the Jordan form or the diagonal form is given by this. P is given by the P are the columns are the eigenvectors of the matrix corresponding to the eigenvalues. And P inverse you can compute. So therefore N matrix which was stated in the theorem can be computed. And finally you can compute the transition matrix. Phi TT0 is a transition matrix, can be computed according to the theorem which I stated earlier. So it finally boils down to this one. Phi TT0 is this is the form of the transition matrix for the satellite problem. Okay, once the transition matrix is known, now I can compute the controllability grammar. Okay, and controllability. Okay. So before that, let us test whether the system is controllable. The satellite problem is controllable or not. Okay, before I compute the steering controller, we can easily make use of the Kalman's rank condition B, A, B, A square B, A cube B. Since the system matrices are constant matrices, we can make use of this LTI result for the controllability. If Okay, you can compute the rank of this matrix, and one can verify that the rank of C is 4, and hence a linearized motion of the satellite is controllable. Okay. Now another question, interesting question is, we ask the following question: what happens when one of the controller or thruster becomes inoperative? Okay, suppose that U2 is 0. Okay, and only U1 is working. Hence, B reduces to that. In that case, if U2 is 0, the B matrix will become a vector. Okay, so B reduces to B1 is 0, 1, 0, 0. And so the controllability, Kalman's matrix becomes B1A, B1, A square, B1, AQ, B1. And you get the controllability matrix as C1, and the rank is 3. That means if U2 is 0, okay, that is U2 is not operating, and you have only one controller, one thruster, then the system is not controllable. So hence the system is not controllable with only the first controller, that is a radial thrusters. So only with the radial thrusters you cannot control the satellite rod. Okay, so therefore the transfers of the tangential thrusters are very much essential. So that is the second problem. Okay. On the other hand, if the radial thruster fails, suppose radial thruster that fails, then okay, if the radial thruster fails, that is U1 is 0. In the case B matrix reduced to this, and this gives a okay the matrix U1 fails, but the U2 is not 0. So you get a different B matrix, which we call as B2. Then the corresponding Kalman's matrix becomes C2, and you form the matrix C2, and the rank is again 4. So the 4, since the U1 was radial thruster and U2 was tangential thruster, we see that loss of radial thrusters do not destroy the controllability, whereas loss of tangential thrusters, okay, it destroys the controllability. Even with one tangential thruster, controller, you will be able to steer the satellite from any initial to any desired final state. Okay, so then suppose that I have an initial state, just typically I'm taking 1, 2, 3, 4 is my initial state. It's not a meaningful numbers, just to indicate they are different. 1, 2, 3, 4 is the initial state, and my final state is 4, 3, 2, 1. Okay, just the reverse of it. I want to steer 1, 2, 3, 4 to 4, 3, 2, 1. Okay, and what is going to be the controller? So UT, by my formula, UT is B transpose, phi transpose, W inverse, okay, into x1 minus phi t1, t0, x0. And if the final time is 1 and the initial time t0 is 0, and for convenience, assume that omega is 1, okay, then that case, you can have a MATLAB code. Now in MATLAB, you can compute W, the controllability Gramian can be computed. These are the MATLAB code, and the U is a controller. Just apply the formula, and controllability Gramian is this one. This is non, okay, this is non-singular, and this tells you that 1, 2, 3, 4 is mapping into 4, 3, 2, 1. Okay, 1 is going to 4. Okay, so 1, 2, 3, 4 is going to 4, 3, 2, 1. So this is the the movement, how the states are moving. And the corresponding controllers, this is U1 and U2. These are the corresponding steering controllers. Okay, so therefore you can steer the satellite from any initial state to any desired final state by applying this control formula. And the formula can be computed numerically also by finding the controllability Gramian. First, find the transition matrix, then controllability Gramian, then you compute U. So by this it is possible. So I think I will close. The time is up. Some references. Okay, a good starting for a beginner to start with such a control theory. A good book is R.W. Brockett, Finite Dimensional Linear Systems, and also a nice book in terms of mathematical description is a Mathematical Theory of Control by Sontag. Okay, and many more references I have given, so one can look into it. And this is all I want to say. Okay, I I thank you. If you have any questions, I think I can answer.
Thank you, Rajagiri George. This has been a very wonderful talk by you on mathematical modeling and satellite control. And if there is any kind of doubt, please put your doubts in the chat box. I hope there might be some doubts. And thank you for all of you participants for attending this talk. And if there is any kind of doubts, please put it in the chat box. Okay, thank you everybody. This is the final session of our STEP talk, and thank you very much, Dr. Rajagiri George, and thank you every participants who've been here. And thank you everybody.
Okay, fine. So good. Thank you for your patience.
Thank you, sir.
Thank you. Right.
Hello, sir. Are you there?
Yeah, I'm here.
Thank you very much, sir.
Okay, thank you.
Yeah, I will contact you.
Okay, sure.